Have you ever just looked up at the night sky and wondered, what are those stars actually trying to tell us? Well, today we're going to become cosmic detectives. We're going to figure out how to read the messages that are hidden in starlight. These incredible messages that travel across trillions of miles just to reveal the universe's deepest secrets.
So here's the central mystery, right? We can't just go out and grab a sample from a star. And we definitely can't visit one. So how in the world can scientists be so sure that the sun is made of hydrogen and helium? The answer, and it's an incredible one, is that it's all written in the light itself.
Now, to crack this cosmic case, our investigation is going to start, believe it or not, right here on Earth. Because it turns out the very same principles that let us decode a distant star are at play all around us, determining the color of, well, everything.
And no, really, think about it for a second. What is physically happening that makes our brains see that flower as red? Is the rose, creating red light? Or is it somehow changing other colors into red? The answer is the very first clue in our investigation. Okay, so here's what's going on. The light from the sun, what we call white light, is actually a mix of all the colors of the rainbow. When that light hits the rose, the pigments in the petals absorb every single color except for red. That red light gets reflected, it bounces off, travels to our eyes, and voila, that's the color we see. Understanding this simple interaction is the first key to unlocking the whole case.
So really, every single interaction between light and matter falls into one of these four categories. Matter can emit light, like a light bulb. It can absorb it, like a black t-shirt on a hot day. It can transmit it, letting it pass right through like a window. Or it can reflect it, just like our red rose. This whole cosmic dance is behind absolutely everything we see.
Okay, so we've got a handle on how light and matter interact. But to really decode these messages from space, we need to understand the messenger itself. Light. What is this stuff, fundamentally? It's time to build out our Cosmic Detectives toolkit.
And this brings us to one of the weirdest but most fascinating truths in all of physics. Light has a dual nature. Get this. Sometimes it acts just like a wave, an energetic vibration moving through space. And other times, it acts like a particle, a tiny individual packet of pure energy. It's both.
We call that little particle of light a photon. The easiest way to think of it is as the smallest possible bundle of light energy that can exist. And every single photon is a tiny messenger carrying very specific information: its wavelength, its frequency, and its energy.
And this right here, this is the most important rule in our whole detective kit. For light, wavelength, and energy are just two sides of the same coin. A short wavelength, like blue or violet light, means that photon has high energy. A long wavelength, like red light, means it has low energy. This relationship is the key to, well, everything that's coming next.
So we have our messenger, the photon. Now we need to find the clues. Let's dig into how atoms leave a unique, totally identifiable mark on the light that passes by them. This, my friends, is where the real detective work begins.
So, inside any atom, you've got electrons, and they're locked into specific energy levels, kind of like rungs on a ladder. They can't just be anywhere. Now, to jump up to a higher rung, an electron has to absorb a photon with the perfect amount of energy to make that jump. And when it eventually falls back down, it spits out a photon with that exact same energy. And it's incredibly precise. Not just any old photon will do.
And here it is. This is the absolute linchpin of our entire investigation. The energy ladder for a hydrogen atom is completely different from the ladder for a helium atom, which is totally different from an iron atom. Every single element on the periodic table has its own unique one-of-a-kind set of energy levels.
What this means is that each element interacts with light in its own signature way, creating what we call a spectral fingerprint. It's like a cosmic barcode that's unique to that element. And this is so powerful, get this. Back in 1868, astronomers studying the sun found a fingerprint for an element nobody had ever seen on Earth. They named it helium, after Helios, the Greek sun god. It was discovered on the sun almost 30 years before we found it here. That's the power of reading light.
All right, our detective kit is complete. We know light is made of photons, and we know every atom leaves its own unique fingerprint on that light. So now, let's put it all together and finally solve the case of what stars are made of.
So when astronomers take starlight and spread it out into a rainbow, what they call a spectrum, they're looking for one of three patterns.
You might see a continuous spectrum, just a smooth, unbroken rainbow, or you might see an emission spectrum, which is bright lines of color against a black background. But the one we're really looking for, the smoking gun, is the absorption spectrum, a rainbow with specific colors missing, leaving behind dark lines of evidence.
And here is the big reveal. A star is a super hot, dense ball of gas, right? So it creates a continuous rainbow of light. But that light has to pass through the star's cooler, outer atmosphere on its way to us. And the atoms in that atmosphere, the hydrogen, the helium, and so on, they absorb photons at their specific characteristic energies. The result? Those dark lines are the fingerprints. They are the stellar barcodes that tell us with certainty exactly what that star is made of.
But that's not all. This cosmic barcode tells us even more. Just by looking at the position of the entire pattern of lines, we can tell if a star is moving. If it's moving towards us, its light waves get all squished together, shifting the whole fingerprint pattern towards the blue end of the spectrum. We call that a blue shift. And if it's moving away, the waves get stretched out, shifting the pattern to the red end, a red shift. It is literally the universe's own radar gun.
And so, just by looking at that light, we can solve the case. The specific pattern of lines, that unique barcode, tells us the star's chemical composition. The peak color of its light tells us its temperature. And the shift in that barcode tells us its speed and in which direction. All of that information packed into a tiny beam of light that has traveled for years, sometimes millennia, just to reach our telescopes.
It's truly incredible what we've been able to learn just by reading light. But it really makes you wonder, with powerful new telescopes coming online all the time, what other, more subtle messages are encoded in starlight? What other cosmic secrets are out there, just waiting for us to finally learn their language?